Here in this lecture, I am going to talk about probability current density. This topic you will find in the subject of quantum mechanics. So, two terms are there. One is called probability density, another one is called probability current density. Okay, the current word is present here. So, what is probability density? Probability density is not, the word probability is involved here, that means it is probability. So, it is the likelihood of finding a particle in space, means at a particular region in space. Okay, it is the likelihood of finding a particle, that means it is also a probability. So, this is called what? Probability density. Next one is probability current density. Okay, this is probability current density, this is a vector quantity, that means it has both the direction and magnitude. It has both the magnitude and direction. And it is what? It is the flow of probability. It is concerned about flow of probability. So, this probability density and probability current density, they are related to each other. And there you will find a continuity equation. Continuity equation of probability density, which is given by this del rho del t plus nabla dot j. This is dot product, okay? Nabla dot j is equal to 0. This is the continuity equation for probability density, where rho, Greek letter rho, represents probability density, not probability current density. It is probability density. And nabla, this is a vector operator, you know this thing. And J, this is probability current density. This is a vector quantity. Rho is not a vector quantity. Okay, that's why I have not put arrow sign over rho. But J, probability current density, this is the vector quantity. This represents flow of probability. Okay, so this probability density and probability current density are related by this equation. That means any change in probability density with respect to time must be compensated by the divergence. This is dot product. That means divergence of the probability current density. Okay, and probability current density is given by this formula. Okay, here psi is there, psi and psi star is there. Psi is what? Greek letter psi. Psi is wave function. And this is the conjugate one with star. Okay, H line is there. This is called a reduced Planck constant, and M is the mass of the particle. So, probability current density is known by this formula. Okay. So, to calculate probability current density, these are required things. Means you have to know the wave function and the corresponding conjugate, okay, of that wave function. You have to know the mass of the particle and reduced Planck constant, that is a constant that is known to you. So, by knowing all these things, you can calculate current density, probability current density, okay. And if you have already studied fluid mechanics, you know that similar equation you will get in the subject of fluid mechanics. There you might have seen del rho del t plus nabla dot v. Okay, v is written instead of this j, v is written v. Can you see this v, capital V? V stands for here velocity for incompressible flow. Okay, for incompressible flow, the equation will be del rho del t plus nabla dot v is equal to 0, where v is the velocity and rho is the mass density, not probability density as in quantum mechanics. That is the mass density for incompressible flow. And if the flow is compressible, then this velocity will be replaced by mass flux. Okay, this rho will be replaced by rho v and this j will be replaced by rho v in case of compressible flow. So that thing you will get in the subject of fluid mechanics. That equation is also called continuity equation, because that represents the continuity of mass. And here in this case of quantum mechanics, this equation represents continuity of the flow of probability, that is flow of mass in fluid mechanics, and here in quantum mechanics it is flow of probability, right? So this was all about probability current density in the context of quantum mechanics. Okay, so this is the end of this video. Thank you for watching this video.